Yeah, Viral, I think you can start the stream now.
Are we live?
No, not yet.
Okay. Hello everyone. Good evening. I'm Astar Rastogi, founding member and vice chair of ACM with Spilani Goa chapter. So today, on the fourth day of our 5-day getting starting with, we have Aaditee Juyal and Ameya Thete for introduction to quantum computing, getting starting with series. Ameya and Aaditee Aaditee is currently working as a Quant Research Mentee at JP Morgan. She has also been working as a Remote Research Intern at Technical University of Munich and has also been a part of Microsoft Engage program 2021. Ameya Thete is working as a Remote Research Intern at the Technical University of Munich. He also worked on UST Global as a Summer Intern. Apart from this, he also holds the gold medal for the iGEM competition of 2020. So in this session, we'll talk about each and every little detail related to quantum computing and its applications. We'll discuss about all major topics in the field ranging from basic fundamentals of quantum computing to its applications in cybersecurity, drug development, financial modeling, etc. We will also talk about learning paths for the field and what are the general practices one should follow. The discussions will be followed by live Q&A sessions where we'll pick up queries from the live chat. Over to you, Ameya and Aaditee.
Hi everyone. Thank you ACM Goa for this opportunity, for allowing us to give everyone an introduction to the world of quantum computing and how you can go about navigating this interesting topic. First, Aaditee would be introducing you to what quantum computing is all about and why it would be relevant in today's area. Then we would be, I would take over and we'll talk about the fundamentals of quantum computing and how quantum computers actually work. Then Aaditee would again go about to take over and then talk about how you can actually get started in the world of quantum computing, because it's a really vast area and it's easy to get lost. So there's just a few tips about how you can get started. And we'll close with whatever work we've done so far in quantum computing and what our personal experience has been with respect to this field. And finally, we'll take any questions that our viewers have. Over to you, Aaditee.
Thank you, Ameya. So now I'll begin with a short introduction of the field. Quantum computing is a new paradigm of computing which emerged in the 1980s. It concerns a utilization of quantum mechanics to improve the efficiency of computation. So it essentially deals with the physical world, which is probabilistic and unpredictable in nature. And it has the potential to solve problems that cannot be solved using classical computation. And it can substantially speed up the process on the problems that can be dealt with classically. Now, quantum computations are based on their own counterpart of binary bits, and these are called qubits. They're used for the storage and manipulation of information. We'll talk a little more about qubits in the later part of the presentation, but the key point to note here is that they can exist in a range of states and not just 0 and 1. Since this sort of architecture cannot be implemented using transistors, logic gates, and ICs, quantum computers utilize subatomic particles as their bits. Now, these bits can be superimposed to give more combinations and can therefore run in parallel using memory efficiently. So because of their ability to create vast multi-dimensional spaces, quantum computers can perform exponentially faster than their classical counterparts. As we've established, some classical problems are intractable, require either vast computational resources or just deal with a magnanimous amount of data. And this could range anywhere from fundamental physical problems such as molecular dynamics or calculations taking place in the Large Hadron Collider to cybersecurity and artificial intelligence to even financial modeling. There is exciting work happening in the field all over the world, spread across different domains. Now, the idea of quantum supremacy suggests that quantum computers can solve such problems in reasonably and exponentially lower time complexities. But we do have to keep in mind that QC provides speedups only to some specific types of problems. And so a lot of time is also dedicated to finding out what these classes of problems are. One of the biggest breakthroughs in the field was when Shor in 1993-1994 developed algorithms for factoring large numbers quickly. And we realized that QC has the potential to process data in an exponentially huge quantity and was therefore capable of breaking cryptographic codes. Now, of course, this is a very crucial point and exhibits the need to be careful with what we do using this technology. And so a lot of research is going towards making a bright future for QC.
Now maybe we'll just, before moving on to where quantum computing is actually used for and what really exciting research happens in this area, it's imperative to talk about how quantum computers actually work, because there's a aura of mysticism that surrounds quantum computers. They're like this black box or a panacea for all problems that we're facing, but that's actually not true. They're pretty simple to understand. Okay, simple might be a oversimplification here, but they're really they're pretty interesting entities. So a fundamental difference that you see in quantum computers as compared to their classical counterparts is the use of qubits instead of a classical bit. A qubit is basically a portmanteau of the words quantum bit, so that becomes a qubit. Qubits are unlike a classical bit where you have like a transistor which is either in an off or an on state, and a simpler analogy of a classical bit would be an electrical switch. So if you flick it on, you're on state, that is 1, or if you switch it off, you're in a 0 state or an off state. That works very well so far. Obviously, we have made really really advances in technology so far, but the difference you see in quantum computers is that qubits are not these electrical switches, or that sort of a entity that you can just switch on and off. Of course, you have values that they can take, like 0 and 1, which also exists in classical bits, but they're much more than that. They're a quantum system in themselves. So at the ground level of a quantum processor, which we'll probably come to later if we have the time, you will find that qubits are implemented using quantum systems that we can manipulate, such as the spin of an electron. A spin is a quantum mechanical quantity which has really no classical counterpart. It's what we call an intrinsic angular momentum to any quantum system. So far, basically, if you're not aware of what spin is or what an angular momentum is, just think of it like a quantity that is characteristic of a particle, something like its charge or something like its mass. Quantum particles also have something called spin, and we have techniques that let us manipulate these systems. So you can, make the spin is like an arrow. You can make it point in different directions. So a qubit is basically this sort of a 2-level quantum system in which your spin on measurement can take 2 discrete values, like how a bit on measurement can take 2 values, that is 0 and 1. That is also the case with a qubit, where upon measurement, a qubit will take a definite value of a 0 or a 1. One other thing what you find with qubits is, apart from these 2 0 or 1 values which you get on measurement, before you measure a qubit, it can exist in a whole range of different states. Calling them values is not really the exact accurate mathematical statement. They're actually different states in which they exist, but for the purpose of this talk, we can talk about them as values. So a qubit basically can exist in different values. It can have different intermediate values apart from just 0 and 1, and that is what quantum computers actually exploit. This property of a qubit to exist in a superposition is what the accurate quantum mechanical term is. That is what is exploited by quantum computers to provide their exponential speed up on certain problems as compared to their classical counterparts. Next, I actually have a slide from IBM research that makes this distinction more clear. On the left hand side, you have a classical width. It can take two discrete values, a false or a zero state or an off state, or a true or a one or an on state. That is pretty much evident over here. An on state is filled in with the color blue and an off state is just black. But on the right hand side, you actually have how you represent a qubit in quantum computing. That sphere which you see is something called a block sphere. Think of it as a sphere of unit radius in 3D space, and qubits are actually points that lie on the surface of the sphere. If you're aware of polar coordinates or spherical coordinates in 3D, every point on a spherical in the spherical coordinate system can be given by three things: the azimuthal angle, the planar angle, and radius. So here you have a unit radius for the vector. So every point lies at a constant distance of 1 from the origin. And then you have and those two angles, theta and phi, which can take different values to have different and lend different value states to these qubits. The leftmost figure provides a more detailed explanation of what's actually happening. You can see that these discrete points on the surface of the sphere are actually different qubits which exist in different values of the single qubit that exists. So every point can be labeled by something called quantum state, and that is what you see over here. You see these numbers that say 0010 and 0000. All of these are labels for a quantum state, and the position, every position on this block sphere has a unique label. And that is how you actually see these are different, because apart from just having 0 or 1 values, they have all of these intermediate values, which is just not possible to have in a classical system. Another thing you can see is on the sphere, the topmost and the bottommost on the z-axis, that is this point over here. I'm not sure if my cursor is visible, but let's try. So these 2 points actually correspond to the states 0 and 1, which are the classical and which are the quantum analogs of whatever you find in a classical system. A thing with the qubit is whenever you measure a qubit, which is essentially a quantum system, it actually just switches back to just 2 values. Which are characteristic of that particular system you're working with. So once you measure a qubit, it can take 2 values, 0 and 1, and these are labeled by the topmost and the bottommost points on this block sphere. Obviously, this is probably a lot to take in at once. There are a few great resources which we'll talk about later, which provide a better insight into how you can actually go about understanding the mathematics behind quantum computation. So another thing what we find is these qubits, when you're doing computations on quantum computers, they're entangled. Entangled as in, which is, if I'm sure you've heard of it, this is a pretty common popular science term where you say 2 systems are entangled, as in without going too much into the details, it would say basically the measurement or the measurement of one of the entities of the entangled system will somehow affect the result you get on the other system. It's I'd probably leave it at this over here, because I don't want to get into the details of the mathematics behind quantum entanglement, but maybe the resources I talk about later would be able to explain that in a better way. So that's cool. So we have qubits, but now what do you do with them? Because just having qubits really doesn't help much. So whatever data which you want to work with, right? So in cases of machine learning applications, you have these feature vectors, or what they're called. They're basically just there are vectors containing numerical values, or maybe if you're working with some other optimization problem, you have basically these values that the function can take. All of these values are actually have to be encoded into the qubit, because we take the encoding part for granted when we're working with classical computation, because the computer just does it for you. Every time you type numbers into a calculator, let's say on your PC, it does everything in the back end, so we don't really realize that there's a bit of encoding that's happening. So the information we're working with is actually being translated to binary, and then it's being worked on those binary classical bits. A similar process has to happen here, but since we're not really that far off into or advanced at this stage in quantum computing, the programmer has to actually encode the information we want to work with onto these qubits. Now there are multiple ways in which you can actually do this. Encoding qubits is an entire research area of its own, but I'll probably give you an example. So what sometimes people do is, whatever value you want to encode, right, that can be encoded as one of the angles I talked about in the block sphere. So if I go back to the previous slide, there are two angles. One is the angle with respect to the z-axis, and one is the angle the projection makes with the x-axis. So these two angles, right, you can actually encode the value into these angles. So let's say there is a number you want to encode. Let's say it's 1.23. You can do some classical pre-processing on it, as in basically you want to make some changes. You don't want to represent it as it is. You want to scale it down to a range, or you want to convert it to different formats, whatever you want to do. So once you have the data which is ready after classical pre-processing, you can actually say, you know what, this particular qubit, I want to set its angle with respect to the z-axis to this number 1.23. So that is one form of classical encoding, a quantum encoding that is done, where you encode the value you want to work with as an angle for the qubit. Because if you see, every qubit over here is described by two angles, which is, as I said, from the polar spherical polar coordinate system. So then there is another way in which you encode the value into the qubit itself, which I'm also not really sure about. So I really won't go into that in detail. So once that is done, okay, so you have entire qubit layout for you to work with. Then you have data which you want to work with. Now that is encoded onto these qubits. Now what are you going to do? So depending on the task at hand, you actually have a series of operations that have to be performed on these qubits. Think of them in your classical computer. You have logic gates. You have an AND gate, you have an OR gate, you have XOR gates, you have XNOR gates, you have all sorts of logic gates. So in a model, so there are multiple mathematical models that you can study quantum computing using. One of those mathematical models, which is quite frequently used and it's also easy to understand, is something called the circuit model, in which we talk about quantum operations in terms of gates, which are not exactly equivalent to classical logic gates, but they build upon that idea. So they have the inputs and then they have an output, and the gate performs a particular classical quantum operation. So these gates actually take in these qubits as input, and then they do all sorts of things. So one could be, you could invert the value of a qubit. So if it's currently in a value of 0, you can actually say, okay, after applying this operation, I want it to turn to a qubit 1, which is equivalent to what a classical NOT gate would do. But then there are more complicated gates which don't really exist in classical computing. So it's like a rotation gate. So you can rotate a qubit about a point, and that makes sense because we just saw the block sphere earlier, and rotating a qubit makes sense because you're just rotating about an angle which you define by the gate. So you have these sequence of steps, which is actually just an algorithm. That is what an algorithm is. It's just a sequence of steps that gives you a desired result. So you have these quantum algorithms that consist of these steps, and these steps are applied either repetitively or just in one shot to these qubits, and they manipulate these qubits such a way that the probabilities of the result you want, basically if you're trying to predict something, using quantum machine learning, which we'll come to that later. You want to basically predict a class. Let's say it's a binary classification problem. There are two classes. You want to predict whether this feature vector belongs to class positive or class negative. What you can do is these algorithms actually have the task of changing the coefficients of the qubit or these angles in such a way that every time you do a measurement, right, the probability associated with the desired class is maximized and enhanced, and the classes which it's not supposed to belong to. For example, if a feature vector belongs to a positive class, the goal of this algorithm, in our case, a machine learning algorithm, a classification algorithm, is to enhance the probability upon measurement of that particular result such that it, upon measurement, produces a class with a positive class, and it tries to minimize the probability of getting the other classes as much as it can. That is basically how most of these algorithms work. There are obviously other ways and methods in which people design algorithms, but these are more common and they're more easier to deal with for a beginner. So that is what a quantum computer quantum algorithm does. It leverages the entanglement you have between all these qubits. As I said, these qubits are generally often entangled. And what it does, it associate, and whatever probabilities associated with these superpositions, right? It tries to change them as much as possible, such that the probabilities of outputs which are desired are enhanced or maximized, and the others of other things which you don't really want. If you're searching for a particular element in a list, that's a pretty common computer science problem. You're given an array, you want to search for a particular element in that list. There is a quantum counterpart for that algorithm. It's called the Grover search algorithm. Maybe once you get into quantum computing, you'll probably have a deeper idea of what the finer nuances of this algorithm and how it works. But you can think of it like as a classical counterpart, quantum counterpart of the classical normal search algorithm. So the goal in that algorithm is to enhance the probability upon measurement of the element you want to search. So after measurement, your algorithm has to output the element it found. And the task of this algorithm is to enhance the probability of getting that desired output, and it has to minimize the probability of getting other things as an output. So basically, that is mostly how these work. And I already covered this thing as basically at the end of a computation, when a measurement is made, the probability of measuring the correct answer has to be maximized. If you've noticed, I keep talking about probabilities here, and I'm sure I should have actually included this earlier, but sure. If people have questions about why am I talking about probabilities so much? So the thing in quantum mechanics is there is not much determinism involved here. Every event that occurs with a probability. So every time you make a measurement in a quantum system, you can say, okay, I will get this particular value, but with this probability. Every time you quote a result, there is a certain probability involved. And since we are actually borrowing topics from quantum mechanics to do our computation here, it's just naturally that you have to work with probabilities in this case too. And next, I talked about gates also. So formally, a gate is basically like a quantum block that performs a specific operation on whatever qubits it acts on. They are quantum counterparts of classical logic gates, but it's not just limited to that. You have many more operations possible in a quantum computer, which a classical computer is unable to do. If you start studying quantum computing, you'll see these diagrams, which I've actually just a figure which I've added. You'll see these quite frequently. So these are actually how gates are represented. The lines which you see, like the horizontal lines, they are qubits. So qubits are represented by horizontal lines, and a gate is represented by either a block, or some gates have specialized symbols like that XOR symbol or a plus within a circle, or you have these filled in circles. So gates sometimes is either represented by blocks, or they have these specialized symbols. So every time you see a symbol on a line, it means that particular gate is acting on that particular qubit. I'll probably just stop talking about gates now. There's quite a lot to cover, but yeah, these are what gates are. Cool. And maybe now I hope you have like a basic idea of what quantum computing really entails or what it actually is. I'd like to spend some time talking about what topics are actually under current research. This is clearly not an exhaustive list, but these are like the most common things you'll find if you do like a simple Google search on quantum computing research areas. First and foremost, the most common thing that comes to anyone's mind when you do research is algorithms or computing research algorithms, because as Aaditee already pointed out earlier, quantum computers cannot provide a speed up on everything. There are specific classes of problems in computer science which actually lend themselves or are amenable to speed ups by quantum computers. So a huge chunk of research in quantum computing happens to find out what problems can be solved by a quantum computer. And then obviously, naturally, the next way to segue into this thing is what are different algorithms you can come up with given this problem is amenable to quantum computation. Then this one is actually also pretty interesting. So there is much research about how quantum computers can actually be used to simulate different physical systems or chemical systems. So if if you've heard of molecular dynamics simulations, they actually just simulate how molecules like nucleic acids or proteins or different carbohydrates, they would behave within force fields or within the presence of each other. The problem with such a computation is even it takes huge amounts of computational resources. It's just very difficult. They run for hours and weeks on end, and it's just basically very difficult to work with. So fortunately, we have found that some simulations can be enhanced by quantum computation. In fact, I'm not really sure which molecule it was, but we have actually been able to simulate the dynamics of a particular organic, biological, biochemical molecule, which was pretty difficult to do on a classical computer. Another thing that has a lot of talk going on is the use of quantum computing in optimization. I'm considering machine learning to fall under this particular area because quantum machine learning is also this huge thing people talk about all the time. So here what you do is you use quantum computers, you develop quantum algorithms that can actually optimize a certain objective function. That's basically the goal of optimization is you have an objective function subject to certain constraints. You want to find what is the best possible values you can get out of that objective function. So this is being used quite a lot. So one thing that comes to mind is the problem of maximum cut, as in given a graph is basically, just think of these as points on a 2D plane for now, connected by lines. So that's basically what a graph is. And let's say these points, right, which are called nodes, and these lines are called edges. Each of these nodes can either take two values, let's say true or false or anything, whatever, any binary value. You want to basically like partition this graph into two sets such that one set contains nodes that completely belong to one class and another set that contains nodes which completely belong to another class. Now, where does the optimization come in? These edges, right, sometimes can have numerical values associated with them called weights. In that case, that graph becomes something called a weighted graph. Now, these weights could actually sometimes denote real-world quantities like bond distances or cost to travel from that one node to another, and it could denote, distances. I think I've already talked about distance, but anyway. So now you want to make this partition such that you want to minimize the cost associated with making those cuts. So that is where the optimization comes in. And a common thing people use quantum algorithms to demonstrate is how you can solve this max cut problem using quantum computers. Now, the next two parts of quantum research, which is error correction, fault tolerance, and quantum hardware, are somewhat related. The issue with quantum computers, which we have now, is that all of these are fairly limited in size. I think 50 to 100 qubits, if I'm not wrong. I'm probably wrong on this, but feel free to correct me if I'm wrong. But it's around 50 to 100 qubits. And that is actually not much considering how we have billions of transistors or billions of transistors in a modern microprocessor. I mean, you just can't compare them anymore. So, and another issue which happens is all of these algorithms work fine when you implement them on simulators. So quantum simulators, we'll come to them later. They basically let you test out. Classically, error correction has become very, very good that we don't have to worry about it when you start programming. You don't really have to worry about your bit changing value. There is a high chance that your qubit will randomly change value, and it can give you all sorts of funny results. You don't want that to happen. So people create these for error correction methods. So basically, these are another sort of quantum circuits that detect if any random flipping or some error has occurred in the computation, and then make changes accordingly in the next round of steps that have to be followed in the algorithm. The issue is these error correction things itself take up so many qubits to work with. The number of qubits you're left with after accounting for error correction is just too less. It's very less, and that currently hinders our applicability of quantum computers to a wide range of domains. Firstly, it is because they're not suitable for every single problem that you can think of, and secondly is also this: our error correction techniques are not great, to be fair. I mean, they are pretty ingenious how people come up with it, but compared to classical counterparts, it's just not good enough. So there's a lot of research that happens where you work on error correction and fault tolerant computation, such that you don't really face any of these errors I was talking about, or faults that creep in because of prevalent conditions. Hardware is also related. Hardware basically involves the manufacture of devices that run these quantum algorithms, because as I've told, you can't really use transistors. You have to use small quantum systems. So these quantum systems are encoded onto like like how you have normal microprocessors. There are quantum versions of microprocessors which you actually like embed these small systems, and these function as your quantum transistors, as if you will. It's probably a wrong way to put it, but helps the point get across. Yeah, that's pretty much what covers how quantum computing works and what topics you have so far. Next, moving on to how you can actually get into quantum computation yourself and start figuring things out for yourself. I'll leave that to Aaditee to cover.
Right. So talking about getting starting in the field, and this is probably something you've realized by now, a huge factor to keep in mind is how fast moving it is and how easy it is to get overwhelmed just by the sheer amount of stuff available. So I would recommend doing a lot of studying about what the field is before indulging completely into one particular part of it. Another important thing to remember here is that because the foundations of this are very anti-intuitive, you will want to spend some time on the basics of quantum mechanics and how qubits work. And you also might want to keep coming back to these every once in a while, especially when you're starting out, because chances are you will get confused and you will forget why something works the way it does. But then again, that is completely normal. Now, coming to the resources available, there is a lot of great material out there. One thing you should try to do is stick to one reference for the foundations, since all of them have slightly different topic flows, and it will be less confusing to follow one train of thought, at least until the concepts click. If you're a student at BITS Goa, you should definitely try to take up the Quantum Information and Computation course, which is taken by Dr. Radhika Watson. This is where both Ameya and I started out. She uses her own book for the course, and it is very helpful. In case you can't take up a course in college, The next best thing is IBM Quantum. They have their own textbook, courses, certifications, and the textbook starts with very basic preliminaries like linear algebra and probabilities, and then it goes up to cover a bunch of important and advanced topics, such as the one Ameya pointed out just now. Once you familiarize yourself with the fundamentals, you will want to start coding. And for this, many software frameworks are available. And these would allow you to simulate, execute, and explore quantum circuits. Again, most of them would require a working knowledge of Python, but I guess that is all right. Talking about IBM Q, if you're using their resources, then much of the material will be using the Qiskit framework. Other frameworks are also available. I think there's Q by Google, and then there's Q Sharp by Microsoft. Any introductory resource you're using will leave you with a bunch of basic algorithms and an understanding of how like the different parts of the circuit work and what the measurements represent. Of course, a lot of this was also covered by Ameya right now. After this, you can pick the field of your choice and start working specifically in it. There is a huge open source community, especially for Qiskit, where they have different repositories for different applications, like optimization, ML, finance, chemistry, and so on. You can learn a lot from these, and once you're comfortable enough, you can even try to contribute to these. Next up, I'd like to talk a little about the opportunities available at an undergrad level. So first of all, there's a lot of hackathons hosted by different quantum computing communities. These range anywhere from universities to research labs. And once again, if you're part of the IBM Q community, they have events happening all year long. So like maybe that is something you should sign up for if you're interested. They even offer research internship opportunities at different levels. So you can do summer internships with them, or you can do your thesis with them, or even at a master's or a PhD level. So one amazing resource for finding opportunities in QC is the GitLab link, which is visible in the slides right now. So I guess it's not updated for 2022. Mostly it has summer positions, but it does cover pretty much every big official position that is available in the field right now at your level. So, right, of course, this is not the only way you can find research work in the field. If there is something you find particularly fascinating that a researcher is working on, you can try to reach out to them via email. And you might not always get a reply since most of these people are incredibly busy, but it is still pretty common for people to find opportunities this way. At least that is how I found my summer research opportunity. So talking specifically about my work, I'm currently working as a remote research intern under Dr. Christian Mendel at TU Munich. So Dr. Mendel is developing a quantum computing toolbox in Julia. It is called Quantum. And as a part of this toolbox, I'm working towards implementing a quantum GAN network, so generative adversarial network. So classical generative learning is one of the most successful unsupervised learning techniques. What it does is it allows us to model and replicate high-dimensional probabilistic distributions using a data set. And when you use a QGAN, you expect for it to reveal some sort of quantum advantage in the process. So what I am currently doing is the generative models for this work employs two neural networks, a generator and a discriminator, which would learn random distributions, which are supposed to be implicitly given by your training data samples. Now, originally, classical GANs were used in the context of image generation and modification. The purpose of a QGAN is slightly different. So we know that quantum algorithms have the potential to outperform their classical counterparts, which is something we probably screamed a couple of times until now. So now the realization of this advantage often requires the ability to load classical data efficiently into quantum states, because you want to solve a real world problem and you want to be able to simulate this real world problem on your quantum computer. And currently, the best known algorithms that we do have would require a complexity of say 2 to the n, if you're using n states to load an exact representation of your data structure into the n qubit state. So obviously, this scaling easily predominates the complexity of the quantum algorithm, and would thereby be like giving you would impair your advantage essentially. So the model I'm trying to implement is a hybrid quantum classical algorithm. The generator of my model is quantum in nature. My discriminator is classical in nature, and it is supposed to be able to provide efficient, approximate quantum state loading. So more precisely, QGAN is used to facilitate efficient learning and loading of a generic probability distribution, which is supposed to be implicitly given by the data samples, and which will then be modeled into some sort of quantum state. And then through the interplay of a quantum channel, maybe a variational circuit, and then a classical neural network, the QGAN can learn a representation of this probability distribution underlying the data and then load it onto a quantum state. And this here would require some polynomial of n complexity, and which would thus enable the use of potentially advantageous quantum algorithms afterwards. Say you could use a quantum amplitude estimation or something like that, whatever you want to do with your data. So yeah, essentially, if you want to know more about like the algorithm I'm working on, there's a link which is available in the slides. My work is based broadly on whatever is theorized there, and it has a lot of interesting applications to finance as well. I believe there is information available about that in the paper itself. And yeah, I think a part of the project would also be to find out some more applications this might have. So yeah, I'm pretty excited about that. I think Ameya can talk a little about his work now.
Yeah, hi again. I started, looking into quantum computation at the end of my second year, where I just taken the course which you talked about by Professor Watson, and that really got me interested into this entire field. Firstly, my work I just went through the Qiskit textbook and tried to replicate as many quantum algorithms I knew about in Qiskit, just to get some idea of how the entire quantum programming thing works. After that, as a part of my PS2, I worked at Infinity Labs at UST Global, where the work mostly involved, replicating results from a previously published paper. It was where we actually took oncological data sets, mostly data sets related to genetic markers of hepatic cancers as well as pulmonary cancers, and then tried to study, just one quantum algorithm for classification task that was a quantum support vector machine. So our work involved, coming up with a new kernel just to use on the quantum support vector machine that would actually give us equivalent or slightly better results on these data sets. The reason for choosing this problem was because we already knew what results we expected. So it was a good, there was already an existing benchmark to compare against, but also just to explore how, that particular algorithm behaves under various conditions, and how changing the encoding circuits or changing how the kernel works will affect the performance. The second part of the study involved trying to figure out whether this actually can be implemented on a noisy quantum backend. So if you're aware, these quantum simulators either let you simulate a circuit on a very ideal backend, no noise whatsoever, but they also have provisions where you can actually just add noises. So we worked with another team at the same place who were developing a noise simulator, and we tried to run our algorithm on their backend just to see if it was, just to see what kind of results it gave. After that, if IBM runs this global summer school, they started last year. So I actually was also part of the summer school last year, where they expose you to more fundamental concepts in quantum computing, and look at a few use cases together. And they have labs and such. So I took part in that too. and so that sort of compounded my interest in quantum computing. However, at the end of this year, once I completed some of my core CS courses, I thought maybe I just pivoted at this point, and I wanted to explore more how classical computation can actually be integrated with quantum mechanics. Not exactly the same as quantum computation, because that you're using quantum mechanics to develop circuits of your own. But here we're looking at classical circuits and see how they perform on quantum systems. So currently, I'm working with the quantum computing group at TU Munich as a remote research intern, where we're focusing on neural network quantum states, where we actually use neural networks to represent a wave function of different quantum systems. So there's a very easy system known as the Ising model, which predicts magnetic properties of materials. So we're trying to create a neural network that can effectively learn the wave function of this particular quantum system, and then try to see if it is also able to predict how if it can evolve with time, because evolution of quantum systems follows certain certain equations or rules given by the Schrodinger equation. We want to see if our network is able to learn those rules as well. So that's what I'm working on right now. So it's not exactly in the quantum computing domain, but quantum learning about quantum computing as it is gives you a new perspective on how other things you learn can actually be used in the domain of quantum mechanics. And you maybe don't have to start out you don't have to completely work in pure quantum computing, but you can borrow ideas from quantum computing to your own whatever projects you're doing with. And yeah, that's pretty much what I'm involved with currently. That brings us to the end of our session. We're pretty much done. Feel free to take any more questions you people have.
Yeah, thank you, Aaditee and Ameya. So we have a few questions. First is how much of a background in quantum physics is necessary to learn about quantum computation?
I'd say I wouldn't say you don't need any background in quantum mechanics at all, because obviously you're looking at quantum physics as it is, but just applied to classical computation. But it's not as much as you would expect a physics person to know about. Maybe if you're a physics major, you really don't have to worry about the requisites. But if you're a non-physics major, I would suggest that maybe half a semester of quantum mechanics should be able to get you to know some basic concepts of quantum mechanics that are required for you to know quantum computing. The IBM quantum textbook as well as the course by Professor Watson cover both of these in beautiful detail, and it's exactly as much as you need, nothing more, nothing less. So I'd suggest you either take up the course by Professor Watson, or you can actually just look at the IBM quantum textbook, which explains these topics really well. If Aaditee has comments on this.
But I think basically same. So you don't really need to know quantum mechanics. Essentially, you don't need to take up quantum mechanics textbooks and then first learn that and then move on to quantum computing. Most of the resources on this are pretty well made in terms of trying to teach computer scientists how to do QM, how to do QIC. So they'll always have a basic background of QM which is needed, and you can just you essentially just need to keep going back to it so that it etches in your mind, and then you'll be able to do it pretty well. Yeah.
However, I can't guarantee this will hold if you go deeper into something like quantum hardware or quantum error correction. In those cases, you need to have a pretty solid background of quantum mechanics.
Right. Anything related to hardware would require more knowledge of the physical systems for sure.
Yes, that makes sense. So, the second question we have is, do you believe that quantum supremacy might cause the modern day encryption algorithms redundant and put critical security systems at an unprecedented risk?
I think that is... Right. So that is a fear, that is a theory. It was something that was discussed widely when Shor came up with his factoring algorithm. So essentially, what we know is that the current cryptographic algorithms are designed in such a way that the cipher which exists, right, a key value cipher which exists, is supposed to be impossible to be cracked in a reasonable amount of time. Which means that if you have a computer which can crunch numbers faster than traditional computers, then there's a very real possibility that that computer will be able to break the cipher and like break down some sort of encryption system.
Yes, fair enough. And we have one more question. What would happen if we try to solve classical problems using quantum computing?
We are actually doing that already. I don't think there's a distinction as such between classical problems and quantum problems, because the distinction is whether a quantum computer can be used to solve existing problems or not. So there's an entire theory behind quantum. There's a theory of quantum complexity theory, which deals with this particular area about whether problems can be solved in a reasonable time by a quantum computer. Which it's actually based on classical complexity theory. I'm sure you've heard of classes like NP or P complexity classes. So it's similar to that here. But we're actually doing that. So, and the max cut problem which I talked about, or molecular dynamics, all of those are classical problems in the meaning of the word classical, because they exist so far. If you're talking about quantum problems as in problems which stem from quantum physics, as in the Ising model which I was talking about towards the end of my section, that also, some of these problems can be simulated on a quantum computer too. So if I think that pretty much covers the answer to that question, because I don't think there's like a separate distinction.
Right. So what you want to do is you want to use either classical or quantum algorithms to solve some real world problem. Now, you might classify this problem to be intrinsically classical. So in that way, say for the algorithm that I'm working on, which I talked about, Hugan, it is used to predict option prices. So or other derivatives prices in finance, which is essentially a classical problem. It doesn't have anything to do with quantum systems per se. So in that way, you can there are some problems which can be solved efficiently using a quantum algorithms and some not, but sure.
Yes, that makes sense. And we have some more questions. Are there any job opportunities in QC, or research should be my main focus if I'm interested in QC?
No, there are lots of job openings for quantum software engineers. So you see the entire Qiskit backend or the Qiskit API that's created that requires software engineers to. It's obviously expected from these software engineers to have some working knowledge of quantum computation. So I'm not saying if you're interested in a career in quantum computation, you really need to focus on research, but that is mostly what the trend has been, that most quantum computing, since it's a very nascent field, in terms of other fields, because even though it started in 1980s, it's still pretty young compared to the other fields in physics or computational theory. So in that way, I'd say most new work that's being done is mostly in research. But there are obviously jobs which don't involve you doing a lot of research. They involve maintenance of these backends and maintenance of these APIs. You need to implement new features in these APIs. So that involves implementing existing results which people have shown, or implementing existing algorithms which people have come up with. So there are jobs there are non-research jobs in quantum computing as well.
Right. And if this is something you want to get into, I believe IBM does offer a quantum development certification, with which you will be you probably will have the skills to do quantum software development. So.
Okay, even I thought that quantum computing means research. So this was a new thing that I got to know today.
Yeah, that's a misconception. Actually, it's the thing is these jobs are not really advertised as much because it doesn't have the coolness factor to it. Because everyone talks about I found this particular algorithm that does this thing. So
You
most
have
of
to
it,
specifically go looking for them.
yeah.
Okay, so a person has asked, I am from electronics background, but I find this field interesting. What are my options if I want to get into QC?
I said quantum hardware. I mean, give if I'm assuming you don't want to get into an IT sector, look at the IT sector over here and quantum computing. I'd say quantum hardware is your best bet. There's a huge demand for good engineers who can construct quantum hardware, and I think that falls under the domain of electrical engineering. There's a lot of work that has to be done in a you say like or to develop a processor that can efficiently emulate quantum systems. So I'd say fault tolerant computation in quantum hardware is where there are a lot of electrical engineers involved. But if you're an electrical engineer who doesn't really like their core subjects that much and you would rather get into IT, but then there's an entire field of quantum programming that's open to you.
Again, there are a lot of job listings available, like especially if you go on to the IBM platform. I think there's more hardware positions than software positions available, especially for undergraduate students. So if this is something you want to get into, maybe you should check that out and read up on the skills required for it, and that would be a good basically aim for you to work on.
So where does IBM open their job requirements on their site itself?
Right. On the site itself. So if you go on the IBM Quantum portal, there'll be a tab which would say opportunities or careers or something like that, and there are quite a few opportunities for quantum computing and on the hardware side as well.
Okay. And there is one more question. How much time do you think it would take for a commercial quantum computer?
I mean, any answer I give here would be highly hypothetical and I don't know enough.
Like in the next 10 years or something, but I
don't know enough to make a sensible comment on that. So I'd refrain from quoting numbers, which will come back to bite me later. So I don't know.
Fair enough. So we have one question. What is the current status of quantum computers and what are the metrics on which they are compared with today's computers?
I didn't catch the last part.
So I'll repeat. What is the current status of quantum computers and what is the metrics on which they are compared with today's computers?
I think we have quantum computers operating with tens, like I think 50 to 100 or like somewhere in the range of tens of qubits. Your metric of comparison would, I believe, still be, I guess, time complexity. I'm not sure. Is that what the question meant? So.
Yeah, the fundamental issue that sometimes comes over here when you're comparing classical and quantum computing algorithms is that time complexity for that matter is sometimes measured in different terms. In quantum computers, you have something called a query complexity, as in you create a oracle and then you measure how many times you need to query that oracle to get your result, basically. But sometimes it doesn't really translate well into classical complexity terms. So that might be a way to judge, but I'm not sure. I think it's mostly the algorithms you propose.
Okay, that makes sense. So a person asked any professor in BITS who could guide you out on this regard. So you talked about Radhika ma'am.
Exactly.
So is there any other professor Not just in
Um,
bits, but like.
Okay, so for BITS, there's Dr. Mizanur Rahman. He's in the math department and he works in quantum information. I did do a project under him last semester. So if you're more into the theoretical and mathematical aspects, like you should definitely with him. As for outside of BITS, I don't even know how to get started with that. I think both of us are working under Dr. Mendel, so definitely him. But
Okay. So there's one more question. If we were to take up a career in quantum computation, what are the opportunities in industry and academia? And like, what are the state of these opportunities in India?
I think as for India, you'd probably find more opportunities in academia like than in the industry. Of course, academia would mean you should go and get a doctorate in a related field and then start working on it. So you could either be working with an educational institution or an independent lab. I guess they do they do some work in quantum computing at TIFR. Again, I am definitely not sure about this.
About this, I'm certain HRI Allahabad and Remote Research Institute in Bangalore do work on in quantum information at least. RRI is purely experiment. I think it's mostly experimental. HRI in Allahabad has, I think, more of a theoretical aspect to it.
I don't think you have a lot of industrial jobs in QC available in India as of now.
Okay. So, like in general, when we think about research, we only think about going abroad, just because like it doesn't have we don't have much R&D in India. So, how much time do you think that it will take to this R&D to come to India, and we can actually think of a future in India as a research?
As far as I'm aware, the government of India has allocated a huge chunk of their research funds towards quantum technologies, the development of quantum technologies in India.
2 or 3 years ago or something.
Yeah,
so
yeah.
you can hope for it to like start showing its effect in a couple of years from now.
But it's difficult to predict. It really depends on the what people are really interested in that particular moment. See, and the thing is, once it becomes an established revenue, it's somewhat like a feedback loop. So once there are established institutes somewhere, people tend to flock there, and then more research happens in those areas, and the other areas get left behind. So, I mean, it takes a while, and I don't think it would be easy to predict for anyone, at least at our level, to predict. How long it will take for Indian quantum the space to come up.
Okay, that makes sense. I guess we are done with all the questions. Thank you for taking out your time, Aaditee and Ameya. It was really insightful, and I learned a lot. I'm assuming that others would also have learned a lot. So thanks for joining us, both of you. And with this, we can end the stream now.
You're welcome. Thanks.
Thank you. This is great.
Also, Aaditee and Ameya, can you share those links that were there in your presentation? So that
yeah. I'll just do it. Give me a second.
Yeah.
The slides is so hard to navigate. I just share them in the chat here. I hope that's okay.
Yeah, that works.
There were 3 links, right? I think there were 3.
I think there's one link. There's another one for the Cascade GitHub repo, like a project.
Oh yeah. Open source. Yeah. I've sent all of those in the chat.
Okay, thanks a lot.
Welcome. Bye.
Bye bye. Have a good day.
Good day.
Bye, you too.
Bye bye.